Good morning and good afternoon, and welcome to our conversation today on densification and the evolution of the RAN. This is part of a report by Senza Fili, prepared in collaboration with RCR Wireless. And today I have the honor to have with me Tom Elliott, the Senior Product Manager at Anritsu here in the US. Tom, thanks for being with us today.
Thank you very much.
So, to get started on the topic of densification, what is that you do at Anritsu personally and as a company?
Okay, well, as far as personal work on densification, I've been heavily involved with, well, essentially redefining just what field test means for DAS. The whole idea of a test as being a return loss or a distance default or something like that really isn't working too well for the DAS people. And we've also had a focus on received signal quality. Myself and others at this company have been heavily focused on the idea of spectrum assurance. The idea that you can have a variety of ways to make sure that your uplink is clean. And with LT in particular, the whole idea of a clean uplink really helps capacity. And capacity is what densification is all about.
Mm-hmm. And so you've been personally more involved into the DAS testing, but I don't read, so you cover other areas as well with respect to densification too, right?
Yeah, personally I've been involved in DAS testing and interference, and others in Anritsu are involved in the exact tests that we do, as well as the spectrum monitoring.
Yeah. Now let's go back to DAS testing. That's a very interesting topic. What is different about DAS testing? Because the end result is we want to make sure that the QoE is good for the subscriber.
Well, exactly.
But I mean, obviously, DAS is a different type of infrastructure. What's different from testing for that?
Okay, well, if you're testing a tower, in installation tested, what I'm talking about here, you'll have cables going up the tower, you'll have antennas, maybe some splitters, other passive RF components. Typical tower test would have 25, 50, 100, maybe even 150 sweeps of some nature. We're talking about return loss, distance default, cable loss, PIM, maybe some fiber test. That can be handled by the existing processes. When you move to a DAS system, especially a neutral host DAS system, where you need to test 3 or 4 frequency bands on every cable, those tests multiply, and they multiply dramatically. A medium-sized DAS install could have several thousand tests. Something like a football stadium, the US Bank Stadium in Minneapolis, for instance, may have as many as 15,000 tests. It's just the sheer scale of the issue becomes a problem. You're talking about months, man-months spent dealing with these tests.
So how can you do? I mean, just the sheer number is just clearly a huge effort. Is it automation going to help this? What can you do? Because the networks are becoming more complex, not less complex, and DAS too. So how are you going to deal with that?
Well, absolutely. And automation can help this. It needs to help it. In manufacturing, for many years, there's been a piece of software called a test executive. It sets up tests, it automates the test, it runs a test, it collects the results, generates statistics. We need something similar to that for the field, something to automate the field test, and DAS is a perfect setup to do this. At the same time, there's the idea of perhaps removing some of the possibilities for error out of these, out of the DAS testing. In the work we've done with some of our DAS installers, we're finding when we come in, there might be a 10% error rate on these files. And what will happen is, say I have 5,000 files. I look at 5,000 files, I can't check every one of them, so I sample. I say, okay, it's good. I pass them off to my end customer. They look at 5,000 tests and say, what am I going to do with this? So they sample the test. And they sample different tests. And if there's a 10% error rate, chances are they're going to find some problems. And then they all come back. And we get into this loop. The problem was expressed to me best this way by one of the guys I talked to down in Florida. I have 1,000 traces in a directory on my PC. Which ones are missing? Yeah, which ones are missing? Which traces are duplicated? Which traces are misnamed? And I haven't even gotten to which traces fail judgment.
Mm-hmm.
Okay. The existing processes, which are based on the tower technique, just do not scale.
Mm-hmm.
Okay.
So how can you moving forward where you have, also the DAS systems are evolving, are becoming more complex with that active DAS and, more moving parts.
Exactly.
How is that? What can you do?
So one thing Anritsu is doing is redefining just what a test is. Okay. I've talked about a return loss sweep, a distance default sweep, a cable loss sweep, and about having to do these all at 3 different frequencies.
Mm-hmm.
Why do we need to run 9 lab-based tests on each cable and deal with these individually? Don't we have computers? Don't they do things like this? Okay, we do have computers and they do things like this. Okay, we can redefine what a test is from here's all these things I have to do to this cable to this cable is good or bad. Okay,
Mm-hmm.
we can remove some of these workflow issues. There's a mop by necessity is fairly general, but when a technician is faced with an ambiguous situation, what they'll tend to do rather than have to come back is they'll take 3 or 4 or 5 different traces and let the engineer sort it out.
Mm-hmm.
Okay. Typing file names on the instrument turns out to be a major time sink. And they not only do they tend to typo once in a while, you would too if it was 20 degrees out and blowing like anything. Okay? Not only do they typo once in a while, but each technician tends to have their own naming standard. And they leave it to the engineer to sort it out. Instrument setups. Again, there's some ambiguity with existing process. And this can lead to, oh my goodness, it was the wrong start and stop frequency, or the limit line was wrong, or something was wrong, we got to go back and retest. These sort of things can be removed by test automation. Okay.
That's also important because when you have well, in a DAS environment, you might have a neutral host, so it's not necessarily the operator doing the testing. Small cells is the same situation where even if it's the operator or a partner, the people that are doing the install and the testing might not be as qualified or have so much RF experience. So doesn't that create additional challenges as well?
It certainly does, and I've been involved in some of these, and just the whole idea of DAS testing, even if you do have RF experience, it's a different field than some of the other testing you may have done, and there are certain ambiguities there. So what Anritsu has proposed is an automated field test solution. You may have heard of it by the name of Skybridge. Mm-hmm. It's on our external website. It provides setup information for the instruments. It provides test automation when you're on site, and it provides automatic judgment, automatic reporting with dashboards so everybody with a login knows exactly where we are. Yeah. This way the questions can be asked and answered while the technician's still on site, before they've closed out, before they've gone somewhere else, before they have to come back, before payment is delayed.
Yeah, so basically you can see there is a problem, and then you can dig down specifically on that. If there is a specific area, or whatever the case may be, you can do it at the same time instead of having a second role.
That's exactly it. The idea is to get things done quick and done now. Our field tests show that Skybridge can cut the actual test time by something like 90%. That's a big number. But if we're going from a manual method to a computer-aided method, that's not surprising.
Yeah, Yeah, yeah. And when there is a huge benefit because you do need to have probably that kind of improvement as you deal with more complex networks. You have to do more testing and more dynamic networks that change more rapidly. So you have to go back and test more frequently, right?
That's exactly right.
Yeah, yeah, yeah. So now you mentioned before interference. How is that? If you look at densification clearly, the more packed your infrastructure is, the more opportunities you have for interference, regardless whether it's inside, indoors or outdoors. How do you deal with that?
Okay, first, maybe I should take a moment and just define what the interference mechanism is, okay? Interference is a receive issue, and I'll get into a little bit of nuts and bolts here, so excuse me. But it's a receive issue. Signals that get to the radio's receive affect the front end. And if it's not the signal you want, it will come in there. It will reduce the sensitivity of your radio receiver. This lowers your carrier to interference ratio. It lowers the radio sensitivity, and it increases your bit error rate, increases your frame rate, increases your drop calls, and all that bad stuff. The name for this is receiver desense, or a desensitization. If it's severe, it's called receiver blocking. And one thing that seems to be a chronic misunderstanding about interference is interference does not have to be on your receive channel. All it has to do is get to the input of your receiver. It can be on a different frequency. In other words, it can be in band, but it doesn't have to be on channel. So your receive pre-filter matters. Okay? If it gets through your receive pre-filter, if it gets to the input of your receiver, it's interference.
And so in terms of the testing, how can you have your testing become more efficient when you are in a situation where you have small cells, where you have this additional source of interference because you have the small cell, you have the macro cell, and they're the same channel.
Yeah, how to make testing more efficient. Yeah. Okay. Anritsu has a lot of interference solutions, but there's one thing I need to point out, and that is signal amplitude at the receiver matters. You're talking about small cells, and I'll point out that small cells have their own unique problems when it comes to interference. Let's say I have a signal source, an interference source, okay? It's at minus 40 dBm. It's emitting at minus 40 dBm. If that signal is a mile from a tower, our propagation says it's going to be something like 96 dB over a mile's distance. It's going to be at minus 136 dBm by the time it gets to the tower. It's not going to be an issue. The tower won't see it. It won't matter. We can coexist perfectly happily. If we're 50 feet from a small cell, it loses 56 dB over 53 feet, okay? Now it's at minus 96 dBm. That's a problem for the small cell. My point here is that when you put in small cells, there's going to be interference sources that will bother a small cell that a macro cell would never see. So interference becomes a little bit of a bigger problem in a way. Of course, the small cell's reception area is smaller. It's a small cell.
Right.
But there's other sources that will matter to it that a macro tower won't see. So the idea of efficiency in finding interference becomes very important.
And I guess it's in finding interference and finding the sources of interference because they're different. So it's not, as you move from macro to small cells, it's not just the area that you cover that is different, is how you interpret the data that you are getting from.
Yes, that's true. So the sort of sources we're looking for, there's on-channel interference, there's interference that's off-channel but in band.
Yeah.
There's impulse noise, arcing, sparking, things of that nature. There's jammers. There's still jammers around. We had a case a while ago where a high school teacher had a jammer running during his test, so his students couldn't cheat. And it was shutting down the AT&T sector. I mean, 911 calls, okay? Harmonics, multiples of an original signal. Some of our TV signal harmonics fall in the PCS band.
Mm-hmm.
Intermodulation, both active intermodulation and passive intermodulation that we all know about
Mm-hmm.
for PIM testing. There's something called the near-far problem, where a strong interference signal or a strong transmitter will overwhelm a weak desired signal. Okay, all of these are typical interference sources, and we've got a great app note on interference hunting concepts that goes over this in more detail, okay?
Mm-hmm.
But as far as making interference hunting more efficient, you talked about that, and Anritsu does have a tool set for this, starting with some of the very simplest traditional methods. We've got the traditional direction finding tools.
Mm-hmm.
We take a spectrum analyzer and a Yagi antenna and look for the strongest signal, and you triangulate. We have map assisted tools that will actually put a map on a spectrum analyzer. We have car-based signal location, where we can go through and essentially seek the power. Do you remember the child's game of hot and cold,
Mm-hmm.
where one child picks something and the other child, are you getting hot, 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 or are you getting cold, cold, cold? It sort of works that way, and it's surprisingly fast.
Mm-hmm.
Also, it's reliable because it takes care of issues with multipath and echoes and reflections and diffraction even.
Mm-hmm.
There is monitoring, because signals aren't always interfering, okay?
Mm-hmm.
So you can characterize the signal, both short-term monitoring.
Mm-hmm.
Every one of our spectrum analyzers are web-enabled. You can hook them up to the internet. You can control them with a browser from a distance, okay? So you can drop something off at a site for a week, for 2 weeks, for 3 weeks, and see what's happening.
Mm-hmm.
On the other hand, you might be interested in some long-term monitoring. We have a set of headless spectrum analyzers designed specifically for this sort of task, which can be either temporarily or permanently in place, and we have software to go with it.
Mm-hmm.
So you can maintain your signal quality throughout your network as things change.
Right. And you mentioned monitoring, and so there is the testing that you do at the beginning, but then monitoring is an ongoing effort. And as you say, interference might be changing, and so the networks are becoming more dynamic. It's the relationship between testing and monitoring evolving somehow with densification and the existing networks that are more complex and dynamic.
So back when we were mostly concerned about coverage, interference didn't matter so much, because all of our cellular standards have redundancy, and they can handle a certain amount of interference without dropping the call. But every one of those methods of handling interference involves sending out more bits to get the same amount of data. In other words, you've hit your capacity.
Mm-hmm.
So as soon as we move to LTE and we're concerned about capacity and densification, all of a sudden interference matters, and it matters a lot because it's hitting your throughput directly. And that's why monitoring is becoming of interest to our customers, especially some of the network operators are concerned about their signal quality and their coverage and their throughput. Mm-hmm. It becomes, if I go back 10 years to CDMA, if we had an interference problem, it would be easiest thing just to plunk a $4,000 board into a base station and bring up a new carrier, and all of a sudden you have more capacity. Mm-hmm. That's not possible with LTE. The bands don't permit it. So if you want to have more capacity, first you need to make the most out of the macro cells you have, and that's what spectrum monitoring is about. Then second, once you get your small cells in, or your IDAS or your ODAS, you need to make sure it's performing effectively.
Right. So now what about spectrum assurance? What is the impact that you're seeing from densification there?
Okay, spectrum assurance is Anritsu's name for a family of spectrum monitoring, interference hunting, and signal mapping tools, both indoors and outdoors. And we're developing this in response to our customers' requirements for exactly the sort of capacity we've been talking about with LTE and densification. That's our response.
Mm-hmm. Right. And what is that you're doing that is special? That?
Oh, as far as looking forward? Mm-hmm. Okay. I think over the future, you can see in general that we're going to be moving closer to real time. We have all this communication capability. Our instruments are using it now, and they will continue to use this. Cloud-based solutions. The test automation for DAS is a cloud-based solution. We're going to see that. You're going to see more remote control. You're going to see more remote expertise. You're even going to see remote dispatch coming in the future.
Yeah, and so what you mentioned real time. What is real time for you in testing? Is it a day, an hour, a minute, a millisecond?
Real time, it can be a day, it can be an hour, it can be a minute. But picture this scenario. There's an engineer at a central site somewhere in the world. There's a technician on site. The technician runs some diagnostics. He posts the results in the cloud. And the engineer sees the results and downloads some more tests to the technician's equipment. That sort of collaboration.
And I guess different sets and different needs, you might switch to different time granularity at the same time.
Absolutely. Monitoring, typically a 15-minute window.
Right.
Okay.
And then
if we're building a DAS system, maybe once a day is enough. Depends on the task.
Right. Now, and this also, the monitoring is, to some extent, you have to fix a problem. So there is a performance problem, you have to go and fix it, but also it allows operators to optimize the use of their network resources. Can you help them with that as well?
With optimizing the network resources? Yes. We do have some, we do have an SPU6 over in Europe that actually has a NOC software that does a lot with optimizing network. So, it does a lot with optimizing network performance. But moving back a little closer, we have a software called Vision. It works with our monitoring, our long-term monitoring probes, and it helps characterize when signals occur, what they look like. It helps figure out where the signals are occurring to within a few blocks by triangulation. And it provides all the necessary information to dispatch a team to go and find that signal. So now when we can sit there in a central place somewhere in the US, characterize an interference on 3 or 4 sectors in, say, Los Angeles, and dispatch a local team to go find it when we're ready to. That's the sort of real-time, continuous, cloud-connected thing we're talking about here.
Right. So real-time optimization, and then also mentioned the cloud or virtualization part. So what is that virtualization? How is virtualization and the cloud changing your solutions?
Well, obviously, our solutions are becoming more connected, and you can expect that to continue in the future. We have a wide world of connection. At least electronically, barriers are falling, as evidenced by this interview. We're many miles apart, and it's working just fine. Yeah. We expect this sort of collaboration in field test to continue. After all, field test naturally has experts in one location and the man on the spot in a different location. And as soon as you do that, electronic communication becomes just a natural solution.
Yeah, and I guess that there are different parts of your testing that are physically still located in different places. So you need to put everything together to understand the end-to-end performance of the network, right?
Absolutely.
Yeah. Well, Tom, thanks for talking to us today and sharing your views on densification.
You're very welcome.
And thank you all for listening in. This was a conversation that is part of a report on densification and RAN evolution that is prepared by Sensafili and in collaboration with RCR Wireless News. Thank you very much.